So I was at the Commercial UAV Expo, which is usually around October, November-ish in Las Vegas, and got to hear what's Robbie's last name? Robbie Hood from NOAA, and was just wowed by the presentation. As we were putting this together, we were picking and choosing, like, okay, who can we get to really highlight this particular industry and this particular industry, and it's been a wonderful experience really finding out, because there's a lot of people in various places that we didn't know about, and we got some of them here today. I'm very excited about that. So actually, our keynote it looked great and then fell apart. We had a NASA, and we're like, oh, that's gonna be awesome, and then it didn't work out. Somebody from NASA Ames, and then we looked at a few others, and we thought yes, and then looked at some more stuff and thought that's not going to work, and I don't want a product pitch. And I've seen keynotes from Parrot Industries and 3D Robotics and Intel, and like I don't want you to be barraged by, hey, we've got the best stuff, product pitches. So on a whim, I was like, all right, I'm just gonna reach out to Robbie and see if by chance she would want to cruise out. She's all the way in, I think, on the East Coast. And she responded the next day and then copied our keynote speaker, who happens to be with NOAA, and he's on the West Coast, which is much easier for us to deal with, not so much travel. So let's see. A lot of really higher end stuff than what we get into in drone technology, which I like to hear from somebody who's got a much better understanding, who does a lot more complicated things than we will probably ever do here on the campus. 80,000 feet is where some of them fly at, right?
Yes, Global Hawk will get above 65.
Yeah, Global Hawk 65,000 feet. So stuff that's way beyond what I'm doing. So Todd Jacobs has been willing to come down, and I'm super excited to hear him speak and share with us today. He's got a ton of slides, so I'm going to start a little early on him. So in case he goes late, we'll hopefully finish just about right. So please give a warm welcome to Todd Jacobs. See if we can translate.
You guys hear me? Is the mic hot?
That they won't hear, but we do.
Oh, okay, that's for the recording.
Yeah, we're going to record it.
Well, I want to thank
Do you want
Mark
me to run this?
and Wing. No, I got it.
Okay.
For having me down, and all the conference organizers and sponsors. I speak at a lot of conferences, some of the ones that Mark mentioned, but I've never been a keynote before, so I'm going to really hope I can wow and entertain you. As Mark said, I'm going to talk about NOAA's unmanned aircraft program, mostly the work that I've been involved with, which is with small UAS primarily, going to remote and hostile environments and operating from ships at sea, supporting science and emergency operations. And but I'll show you a little bit of the big stuff that we do, most of that in conjunction with NASA. I've been with NOAA for 27 years, been involved in a lot of technology infusion, unmanned systems in the water, on top of the water, manned deep submersibles, and I've been working on unmanned aircraft issues since our program started with a project, Flying Predators with NASA in about 2004, 2005. I'm a former San Diego resident. I did my undergrad at San Diego State, and I worked for about 3.5 years as a science diver just out here off of San Onofre, doing some of the tail end of the environmental impact studies that were on the power plant. So it's neat to be back here. So I really got the program kind of put into two parts, kind of like prehistory, what we got to, what issues we went through, evolving equipment and some relationships with manufacturers to meet our specialized needs. And then kind of the most relevant stuff, the stuff we've been working on the last couple of years and what's important to us. So if any of you go to the big drone shows over the years, you'll hear the 3Ds, dirty, dull, and dangerous. Well, I really offer that there's a fourth that's most relevant to us, and that's a sort of denied access. Areas that are really, really hard to get to, that you can't get traditional survey aircraft to, or situations where you're flying under the weather. You know, you're able to conduct surveys in foggy conditions or below a persistent cloud deck. Areas where you're operating in conjunction with wildlife that's very sensitive to hazing. to noise and seeing planes go by. And so we've adopted drone technology for a while now. Also, there's some instances where it's just dangerous to get people ashore from our ships to do surveys, where we can actually do them from the ships now. So we've taken a tack where we've really purchased and adopted and adapted a lot of military hardware, which is more expensive than a lot of the systems that you all may be using or have been exposed to date. But for us, we really think about how we get there, and the most remote places we go, we get to on our ships or on Coast Guard icebreakers. And those ships cost between $25,000 and $100,000 a day to operate, plus the personnel. So the cost of the system, if it works, if it's durable, if it's robust enough, if it can operate in those conditions, is kind of a rounding error in the background. So that's a constraint that we haven't really had for some of these things that you all may look at. So the big stuff, as I mentioned earlier, we really do in partnership with NASA, and we operate routinely the Global Hawk and on occasion Predators for science missions. The Global Hawk work, which I think Mark referred to and probably heard Robbie talk about it at length, Robbie Hood's the director of the NOAA UAS program, is mostly global climate change research and hurricane research. And traditionally, NOAA's flown our P3 hurricane hunters into the eyes of the hurricanes. We penetrate the eye wall to get hurricane data, in addition to flying around them with a G4, a Gulfstream jet that's heavily instrumented. And there's been a couple of close calls over the decades doing that. And we're hoping to sort of move a lot or all that mission off to unmanned aircraft. And the Global Hawks that are flown are demilitarized, sort of excess, really obsolete models that we've gotten from the Air Force. The Predators, we've really the best and highest use for those, although they're very expensive, is for surveillance of vast marine protected areas, looking for fisheries violations and foreign fishing incursions. Although we have tested them for some science payloads, there seem to be better ways to go for a lot of what we're doing. Just so you can see what it looks like to operate a Global Hawk, this is at NASA Armstrong Flight Research Center on Edwards Air Force Base out in Mojave, the G-Hawk Ops Center. You see the glass wall. In front of that wall are the people operating the vehicle. And there's about a dozen of them involved in flying it, monitoring the radios, the comm links, power, navigation, etc. And then the back is the science party. And there's one liaison that talks from the science team into the flight crew so that it's not just mayhem. And there's 3 Global Hawk Operation Centers now for the NASA birds. One is at Wallops on the East Coast, out in Guam, and this one. And they can basically fly anywhere in the world from those 3 places and loiter for hours and hours. They can fly for almost 40 hours straight, a 13,000 mile range, and can haul almost a ton of payload. So that's just a sort of primer on that. But we haven't seen, even with the smalls, where you're really taking the man out of unmanned. Even the Puma systems that we fly take a couple of people anyway, and usually 3 with a scientist in the loop. So some of the other systems we played with over the years and done specific missions with, this is kind of in the medium range, just under 55 pounds, are the then ACR, now BAE Mantas, shown in the lower right there. We've done some work with the ScanEagles in the Arctic, especially from ships counting seals. We really focused on which would be the best small unmanned aircraft system to operate from our ships. And that was after testing a whole lot of stuff over years, and came up, for starters, with the AeroVironment Puma AE system, because it was built to support the Special Operations Command and the Army. It can land and survive being in the water. And I argue that it's pretty easy to take off from a ship. It's really hard to get things back. And unless you have something that's either at a price point that you consider expendable, whatever your budget is, or it's waterproof. I can tell you, after almost 30 years of going to sea, everything ends up in the water eventually. So we cut our teeth on the Puma, and I'll show you some pictures here in a minute of a lot of the missions that we have tested and developed and sort of adapted the Puma to do for us. We also do some work with vertical takeoff and landing, VTOL equipment, some of them custom built for our needs. There's a group actually out of our La Jolla lab that goes all over the world with some custom built equipment. Oh yeah, a couple more things. Yeah, early hurricane stuff with Aerosonde, whale watching stuff, whale survey stuff in Hawaii, probably 2004 or 5 here. This is back in the days before they even came up with the small UAS rules from the FAA, and we'd go out with a couple of baseball caps and trade for an airfield for a week, you know. And so you're sort of seeing, you know, the Wild West, then the clamp down of where it's really hard to operate in the NAS, and now things, at least low-hanging fruit stuff within visual line of sight in the daytime, obviously, are getting easier to do. This was some work we did with Scripps Institute during the Chinese Olympics when they shut down a lot of the production of China, and we were looking at air quality in the Maldives, Hawaii, and the West Coast here to look at, help Scripps operationally look at how air quality changed when China's black smoke was not going out the stack. It was an interesting project. Again, this was back in 2007, and it was really the ScanEagle and the Puma that could operate from a vessel, and it really still is. You know, it's kind of funny, but 10 years later, there's really only a couple systems that can be reliably operated from vessels. This was a ScanEagle operation, kind of first time we took them to the Arctic, and had some success. I already mentioned the VTOL stuff. Couple problems operating from boats. Magnetometers usually wig out on the steel decks. A lot of times if a VTOL, depending on the system, takes off while the boat's pitching, they fly crooked. We've had a few systems that can sort of zero out and deal with that, but I haven't seen any reliable waterproof stuff yet. And we're starting to work with industry now and have some SBIR grants. So those are grants from the federal government, go out through NOAA, to develop equipment that can handle the marine environment, that takes off vertically and then transitions to level flight. We're looking for some equipment that can fly off of our non-helicopter flight deck equipped research vessels. We have about 17 research ships that go around the world. So I mentioned the Puma, small footprint. You can see the Pelican cases there on my left, your right. That's a whole system. Everything you see here in the screen, hand launched, recovered after a deep stall into rocks, water, sand, ice, snow, whatever. Been pretty reliable. We operate mostly from sea, easy to launch, various schemes to recover. When you have a small boat, it's not too big a deal. You can back the boat up to it, grab it. So I'm talking up to a small research vessel, something up to maybe 70, 80 feet. When you get onto a ship, whether it's one of our 200-foot long plus NOAA ships or a 400-foot long Coast Guard icebreaker, it starts to be dangerous in ice conditions when you're putting people down 50 feet into a rigid hull inflatable to go pick up your 13-pound airplane, right? And you don't want the 200 or 400-foot long ship tending the airplane. It just doesn't make sense. So we started to work on how do we recover reliably aboard the ship. Some slides with that. Other adaptations that we've worked on besides recovery on board the ships is data exploitation. So the first level is having the scientist in the loop so that they're really helping drive the camera, essentially. So when we're on a boat, we have various size from 12-volt color high-resolution TV monitors we can take into the field. If we're on a ship, biggest TV we can plug into. When we're on an open vessel in bright conditions, we've adapted gamer goggles, that you can get. And so, it stops down so you can see the screen even in bright ambient light. The only problem with that is if you're prone to seasickness, you're probably going to hurl all over the place. So it takes a special person to be able to handle that. But, that's really the scientist's role here is to direct the camera operator to pan up, tilt, zoom in, snap the still, go around again, etc. We've also exploited, especially for law enforcement purposes, the remote video terminal, where we're sending a downlink to the vessel that's actually boarding other vessels, so that not only can the people on the boarding boat see what's going on the boat they're about to climb up on, but so can the people on the command ship. So it gives everybody sort of peace of mind, especially at night. And then there's data out. And so on this slide, you see antenna array on top of Santa Cruz Island. And we're working here with the NOAA research vessel Shearwater and an 87-foot Coast Guard cutter. Here we exploited a local microwave internet link to send our data, bounce it off Santa Cruz Island, off the microwave link back to the internet, and it was shared, at an incident command center and around. Since we've exploited Inmarsat and other satellite comms, KU bandwidth, depending on where we are, to send real-time incident information into incident command centers. And that's sort of a next level, but an important link, I think, at least from the remote areas, especially disasters. So I'll show you now some pictures of some of our sort of natural resource kind of testing and some of the things that have become operational. This is an amazing picture of a blue whale about to be tagged. We're flying below a 300-foot cloud deck, 35 miles offshore. So even if you had a helicopter out there, they'd have to go back for gas every couple of hours, be beating up the water. There's a remote video terminal on this rigid hull inflatable. On the bow of the prow of the rigid hull is a scientist with a suction cup tag. And they're able to see from our lead when the whale is going to come up to breathe, so that they can get right up next to it, get that tag on next to the dorsal fin and back off without touching the whale, except for the suction cup tag. Plus, we know that's a 20-foot long boat. You can scale the whale. You can verify where the tag was put. So these are data that you couldn't get really any other way. And it makes this choreography, this dance of tagging a blue whale take maybe 15 minutes instead of hours sometimes. So one example of things you couldn't do otherwise. Seabird surveys, remote colonies on cliff faces in really sensitive areas. That was the Olympic National Park. Pinniped surveys. A lot of the work we've done off of California, Washington, and Oregon, we prototype for really remote places. So we take the California sea lions, the rookeries on the Channel Islands. They're great analogs for Hawaiian monk seals that are the most endangered pinniped in the world that we survey out in the Northwestern Hawaiian Islands archipelago. Basically everything northwest from Kauai to Midway, 1,250 miles, northwest of Kauai. So we've been able to do a lot of our work, including beyond visual line of sight testing in military airspace. So we're able to schedule military whiskey and restricted areas so that we can actually prove things before we go remote. Enforcement and surveillance, as I mentioned earlier. The black and white shot's an IR shot of a squid fishing boat working at night. So it's a task force with Coast Guard, Cal Fish and Wildlife, National Park Service, and NOAA, people sighting squid fishermen fishing in marine reserves at night. After the big the big Japanese tsunami in 2001, we did some testing to see if we could actually see marine debris in the water before we went remote out to the garbage patch to try and quantify it. So the gyre out in the Pacific. So this was some testing of that stuff. And oil spills, I mentioned emergency response, both search and rescue and oil spills. I think they're great applications for small UAS. A couple of the things that are really wonderful is you can quantify things. So here you're seeing fluorescein dye in the water as an analog to oil, because they actually don't let you put oil in the water, believe it or not. Unless you go to Norway. But what's neat is you see this line here with the S and T. So you can actually put this transect line out and measure it and quantify, how big a patch you're looking at in the water and how it's changing and how it drifts. And traditionally, this is done by a pretty well-trained person hanging, their head out the window of a Coast Guard helicopter, guesstimating. And so it allows you to make sort of a more quantitative estimate. This is some early stuff. The resolution's a lot better now, but we're also now have protocols to use small unmanned aircraft, both VTOLs and fixed wing, especially in remote areas, for our natural resource damage assessment. So quantify oil on the beach wildlife in there. We were doing a lot of work in the Arctic for a few years while Shell was still planning on putting that drill rig up. That plan's now indefinitely on hold, but still, it's sort of like when, not if, there's going to be a big oil spill in the Arctic, because we've seen cruise ships up there now. The inside passage, of which there are a few routes, is now being exploited by China. It's the fastest, most efficient route when it's open, when it's ice-free, when there's little ice, from Asia to Europe for trade. And these are hugely sensitive areas. And so we started in 2013 working with the Coast Guard with off-the-shelf stuff to see, what can operate in those conditions, what can we learn. Well, we learned icing's a problem. That it takes a lot of skill, to operate in a very dense, cold air. That we have to work a lot on communication with all the science parties working out there, deconfliction. And so we went back the next year, and we also realized that we had to catch the air vehicle on board the ship, as I mentioned. And so we brought up the next year, 2014, we had included new objective, including not only capturing the air vehicle on the ship, but also that we needed to fly to be effective beyond visual line of sight. So we worked with our own folks, the Coast Guard, to exploit due regard authority, which some federal agencies have, to sort of self-deconflict in remote areas. We only flew a mile. We still flew within visual line of sight, but we used a different authority, which we exploited further next year. What we did realize is having a net to fly into was viable, but it took so much skill we needed to have an autonomous system. So we worked with the manufacturer to develop that for next year. There's some pictures of that kind of work. And here's what our initial net capture system looks like. We exploited a smaller net that could be adaptable on NOAA research ships. That's the triangle one. When we're on a flight deck equipped ship, like is shown on the lower right, there's a net that goes all the way across the deck, which is a lot easier to hit. So a lot of the work we prototyped, as I mentioned, was for this Northwestern Hawaiian Islands area, so one of the most vast and remote areas that we manage. It's over 500,000 square nautical miles of water. In 2014, we had sort of a comparison. We had an opportunity to fly a NASA Predator out there, along with the Puma. So I took the Puma system out, and you can see all the way to Midway Atoll, almost at the end of Kure. That's the extent of that area. And we left from Honolulu on a NOAA ship. Simultaneously, we were setting up NASA's MQ-9 Predator B, Ikana is its name, in Kauai. And so it supported a couple things. You can see from a science perspective, the data is about the same, actually, with the resolution that we were getting. The Puma camera's a lot better. But from being able to find ships and unwanted fishermen, there's nothing like that Predator. It can scan really 100 miles wide with a synthetic aperture radar, and then it slews over the optics and lets you pick it up. There's operating from a small boat, again, with our goggles and stuff, and from a ship. And these are what the data look like. So you can go in and count monk seals and turtles without having to land people through the surf on the beach. The initial resolution was enough to count animals, but not to read their markings or figure out if they're male or female. We got to that a couple years later. Same problem with the birds. The original payloads that we were looking at didn't have the resolution to tell us if they're juvenile or which species. Marine debris also, we're looking for buoys and things and nets that are removed by our teams every year. Just a few significant events I'll go over. But the past year, we've been really looking at, or I've been looking at, operating beyond visual line of sight. That's a big part of what we need to do. Working with industry through agreements to develop something called CRADA, Cooperative Research and Development Agreement, which allows us to partner with industry to provide resources back and forth and expertise and personnel. And really working on getting data where it needs to go from the field in real time and near real time, and our data exploitation. We got an opportunity to work on an oil spill. This was a precedent where we were working in conjunction with manned helicopters, 2 of them, in real time mapping during the Santa Barbara oil spill off Refugio. some pictures of that. And we produced a 2.5 centimeter per pixel map of the oil spill using unmanned aircraft working, within a mile of people in helicopters. This was a precedent. It took a lot of front-end coordination. It was done within a temporary flight restriction zone. There's the oil on the water, the incident command center. You see the TFR. Then the other ring is the Santa Barbara Airport, which is the 5-mile ring that you have to stay out of. So that's what the final product looked like, Refugio Bay. And if you drill down, you can get to any individual rock to figure out if it's wet or oiled. Fortunately, I can't show you a resolution beyond this because it's embargoed for litigation. But that's basically we go down ships, we vector small boats from big ships to go find turtles so they can be captured in census. Those are the kinds of things we do. Then back to the Arctic, working with industry. Now we're looking at de-icing of wings with a carbon nanotube paint that's heated, relaying long-range line of sight through an aerostat, and more operating in real time with helicopters. This is a search and rescue drill off Wainwright, Alaska, with a ScanEagle, a Puma, and 2 rescue helicopters that are searching for the unmanned aircraft found and then vectored into helicopters to an aviation life raft with a warm torso, not a human, but a battery-operated thing. And again, this is about as remote and hostile as it gets, but we're, again, safely deconflicting in real time with manned aviation. It was really hard to find that life raft, even with IR. And my takeaway was, after 3 years in the Arctic and once in Antarctica, is don't fall off the ship. If there's one takeaway from this. But this was neat because we operated due regard. We went 5 miles beyond visual line of sight. That was an arbitrary number, but it allowed us the next lead, which I'll show you in a second, when we went to Antarctica, to 25 miles beyond visual line of sight, helping the icebreaker navigate around bergs and big obstacles on the way down to McMurdo, Antarctica. So now, wrapping up, sort of state of the art, higher resolution cameras, being able to do 2 and 3D mapping with LiDAR and precision nadir camera. Went back out to the Northwestern Hawaiian Islands a couple summers ago, testing a prototype imaging system, made 3D maps of some of the atolls that will be used for baseline for global climate change, sea level rising. And we got to this kind of zoom now. So I know that that's my colleague Katie walking on the beach by a 5-gallon gas can. We're at about half a mile slant range, 2,000 feet, flying back towards the ship. Now watch this zoom out. Oh, there's the whole atoll. Right? So that's what the state of the art is getting to now, and it's getting really interesting to us as scientists. This is just an image from a video. Now I can tell you that that's monk seal number 207. And we were able to produce all those maps. There's a ship we took out and a plane we flew back to Honolulu. So you could not get to those places in a high-wing, slow-flying survey aircraft with cameras in the belly. It's too long a range. So again, things that you couldn't do otherwise. So we went down to Antarctica. It's a 2-month trip, supporting the Coast Guard for their annual Operation Deep Freeze on the Polar Star. It's one of our 2 operational icebreakers. They didn't bring a helicopter. We wanted to see if we could help the ship navigate and to help validate and ground truth the satellite images of the ice pack for the National Ice Center. So usually my team is directly supporting science by collecting data. This time we were supporting the Coast Guard operationally, who was supporting science by opening up the ice-free channel to resupply McMurdo for the year. But they asked us if we'd go based on our successes in the Arctic, and we said, what the hell? It was a hell of a trip, the harshest conditions we've ever worked in, both physical and regulatorily. The National Science Foundation wouldn't let us operate within 50 miles of a manned aircraft, even though we'd been within a mile of helicopters in the Arctic, months before. So if a C-130 was taking off for Christchurch over here, we couldn't fly at 300 feet over here.
And so we got relegated. A lot of our work, once we got into McMurdo, our real job was done. We could only operate between midnight and 6 in the morning. But it was beautiful. It was amazing. We were able to develop and perfect our protocols for operating in those kinds of conditions. We tested this new payload that we've been waiting for so long to really make sure we work in the Arctic conditions, in the Antarctic conditions. And as I mentioned, we did a record-breaking 25-mile flight from the ground control station, which allowed the icebreaker to figure out whether or not it could go refuel the helicopter supply station down in Antarctica. And we performed missions that you certainly couldn't have or wouldn't have wanted to try with a helicopter. So that's kind of the end of my slides, and I'll just leave it at, for what we're looking at doing, what we want to see in the future is more equipment that can operate, at least for our little niche, in the conditions that we operate in. And I see really the biggest advances coming in VTOL and transition to level flight, making it easier to make products and derivatives out of those data. And I think the regulatory scene with transponders being micro-sized and battery power getting better, is going to, the commercial market's going to bring a lot of that to bear. I think that's just about 29 minutes, so I'm going to cut it off there.
You got any rapid fire questions you guys got for him? Yes.
How did you know that was seal number 207? Just the resolution of the image?
Oh yeah, I'm sorry if you couldn't see it, if it was too bright in here. Yeah, they're 4-inch bleach marks of numerals, and that was seal 207. That was that seal's number. You could read it off that image, at least in a dark room. Yeah.
You mentioned landing a drone on the net, like that. What if you had like drones and you had the drones hold the net and pull it out, so you could land the plane on it?
That's an interesting idea, although they'd have to deal with the wind and everything that the main drone that was approaching would. I think that ScanEagle, Boeing in situ ScanEagle, has a scheme that I saw at Exponential last year where they actually have a VTOL bring up the cable, and fly the ScanEagle into the cable. So that would be for if your ship doesn't have the room to have their regular recovery system, which comes off a boom crane. But to me, things as they evolve should get more clean and simple. And that seems like sort of some of those things, like you're introducing more potential points of failure. So I like to keep it simple, stupid when we go to remote places.
One more. Go ahead.
Are those gas powered, or are they like the drones that you were flying in Antarctica?
Those are those are battery powered, and they have a 3.5 hour long battery now. And we actually seem to be able to get that if we keep them warm. So we keep them warm, in the cabin until we're just about to take off, and then the battery generates some heat while it's being used and seems to maintain itself. So we're getting almost full expected battery life like you get in temperatures around here in remote places if we care for the batteries correctly.
That's the other area. You're going to get one more? I'm going to cut off. Okay, you said one more.
Real quick, just since you say that was the batteries, are they starting anything with little mini solar panels to prolong the flight time?
Yeah, there is a solar Puma that AeroVironment's developed a wing that they've flown for like 13 hours or something like that on the recharging itself, keeping it running off solar. Although a lot of the conditions we fly in, we don't have sunny conditions 1 and 2. I don't think they've waterproofed it yet. Yeah. But that's something that they're looking at. Thank you.